I want you to allow me to mathematically acquaint you with the idea of creation of imaginary numbers. Beginning with the set of counting numbers, which is the set of naturals, if I consider the equation x plus 3 equals 2, where 2 and 3 are natural numbers, and because 3 is greater than 2, in the next step I get x equals 2 minus 3, which is negative 1 as its solution, which is not a natural number. This implies that there is no natural number which is able to satisfy this algebraic equation, or in other words, this equation has no solution in my available set of numbers. In order to make this equation solvable, the mathematicians decided to extend the set of naturals to a bigger set of numbers, which is the set of integers. This set of integers, apart from consisting of the naturals, also consisted of new numbers like 0, -1, -2, -3, and so on. Thus, any equation belonging to this family, which was not solvable in the set of naturals, was uniquely solvable in the set of integers. Cool? Next came up the equation which looked like, let's say, 2x equals -3. In here, 2 and -3 are integers, and because 2 is not equal to 0, I'm going to divide both sides of the equation by 2. This in the next step gives me x equals -3 by 2, which is certainly not an integer. So if I confine myself to integral values, then this equation has no solution in the set of integers. See, right now at this stage, set of integers is my largest set of numbers available with me, and this equation is not solvable in the set of integers. In order to make it solvable, this set of integers was further extended to get the set of rationals. Okay? And thus, any equation belonging in this family, which was not solvable previously in the set of integers, happened to be uniquely solvable in the set of rationals. Are you understanding? Now, next was the equation which the mathematicians encountered, x squared equals 2. Well, at this stage, the biggest set of numbers available was the set of rationals, and this equation was not solvable in here as well. Why? Because there is absolutely no rational number whose square is equal to 2. It was at this point that the term irrational numbers was coined, and they were defined to be just those numbers which are not rationals. Okay? So on solving this, you obtained irrational numbers to be the solution of this equation and not rationals. So such equations, or basically equations belonging in this family, did not have any rational number as its solution, but had irrational numbers as its solutions. Right now, the set of rationals was further extended to obtain an even larger set, which is, the set of reals, which consisted of rationals as well as irrationals. So did you see? As and when the need arose, the mathematicians extended the existing set of numbers to obtain even larger and larger sets of numbers to provide solutions to such algebraic equations. Till now, or I should say as of now, how much ever we've studied mathematics, you guys would be aware of R to be the biggest, the largest set of numbers in the number system available. Right? So, is it like there is absolutely no set of numbers bigger than R? Basically, what I'm trying to say is it like the extension process stopped at R? And hence, I should declare R to be the biggest, the largest, and the final set of numbers in my number system? Because that can only happen when each and every mathematical equation gets solvable in R. Is that true? No, there's not one, but in fact, there are infinitely many mathematical equations which do not have any solution in the set of reals, even when the set of reals is a massive set of numbers. And the very first such equation is x squared plus 1 equals 0. Let's justify why this equation is not solvable in R. See, you take x to be any real number, its square is going to be non-negative. Non-negative plus 1 is certainly going to be positive. Never 0. Okay, that means there is absolutely no real number which is able to satisfy this equation. Isn't it? Or in other words, if I rewrite this equation as x square equals negative 1, then if x is any real number, its square is always going to be, as I said, non-negative. There is no real number whose square is a negative number. Hence again, there is no real number which is able to satisfy this equation. In fact, if you forcefully try to solve it to obtain its solutions, you get x equals plus minus under root negative 1. And you know, square root of only non-negative numbers exists as a real quantity. Square root of negative 1, basically square root of any negative number, doesn't exist as a real quantity. It is not defined in the set of reals. So now I'm sure you are convinced to believe that yes, this equation doesn't have any solution in the set of reals. It was at this point of time that the mathematicians realized the need to extend the set of reals to incorporate more new numbers so that such equations can be solvable. And in that quest, the very first new number which was introduced was by this great mathematician Euler, and it was iota. It was denoted by the symbol I, and it represented square root of negative 1. Yes, you know, square root of negative 1 is not a real number for sure. This non-real quantity was called the imaginary unit. So how did the introduction of iota help us to obtain the solution of the equation x square plus 1 equals 0? How? Well, you know, if I write this as x square equals negative 1, and in the next step I write it as x equals plus minus under root negative 1, now I can replace this under root negative 1 by iota. And bingo, plus iota and minus iota are its two explicit distinct solutions. So there is no real number which happens to satisfy this equation, but yes, there are definitely two non-real or imaginary numbers which are able to satisfy this equation. So this equation is solvable not in reals but among the imaginary numbers. Understood?